do pipx run build, for example. Or there's also this nice GitHub action, Hynix GitHub build and inspect Python package. Use that, and it produces your sdist and your wheel for you. But this is a little more complicated if you have binary packages. So I really see this as having 3 components that you have some way to write your bindings. You could use the CPython API, or you could use a binding tool, which often makes things easier. You have some sort of build configuration, and then you need some tool that builds mini wheels designed to run across different platforms. We'll focus on this middle area today. 2 years ago, I gave a talk, and I focused on the other 2 pieces. And I kind of said that a lot of work was happening in this middle piece, and I kind of apologized that it was not in better shape, and now it is in better shape, and I'm going to tell you about it. But we will talk a little bit about the mini wheels part 2, so I want to give a quick update on CI build wheel. So CI build wheel is a tool written in Python that allows you to build redistributable binary wheels across all the commonly supported platforms. On the right, you see the GitHub setup. This is you could actually stick this in a GitHub Actions file and use this. And this will build across Mac, Linux, both flavors of Mac OS. And then I would recommend at least a little bit for further configuration in your pyproject.toml file, which you see on the left. And that will tell CI build wheel to install that wheel it built and run your tests. And so you can give it a command to test, and you can also tell it what to install for the tests. Okay. If you want to run this locally, because it's just a Python program, you can. It's not, even though it has CI in the name, doesn't mean it has to run in CI. You can do this on pretty much anywhere. So for example, you could do pipx run CI build wheel -- only, give it an identifier to tell it which wheel you're trying to build. And this will, for example, build the PyPI wheel for 3.10 on Mini Linux. And you can run this from Mac or Windows as well. So a few features that have happened, that have been added in the last couple of years. We currently are supporting Python 3.13. That came out earlier this week. We have an override mechanism that got a bit more advanced. You'll see some examples of something similar later. We've updated a few things. And of course, we support the new Apple Silicon runners. Some things are currently being worked on. Free threaded support should be coming very soon, so by Python beta 2 at least, maybe sooner for some platforms. And we're investigating UV support for faster builds. Okay, so going back to this configuration, to how you set up your build. Before all of this happened, we had setuptools and distutils. And in order to write a .c file in C and to build it, it looked like something like this. You'd have a setup.py, and you'd put this sort of code in it. And this works. I haven't put in the manifest.in, so that file won't actually show up in your sdist, but ignoring that, it works. But there's a bunch of things that you might want. For example, you might want to use third-party dependencies. I would say that's one of the biggest ones. Or maybe you want to target a specific C++ version, like C++11 or C++17. There is a way to tell it to do C++ at least. Or maybe you want to have multiple files compile in parallel because you have more than one file. Or you might want to have some sort of caching because this takes time. Or there's a variety of different things you might want. You might want to load up your IDE, and you might want it to be smart about figuring out where everything is and give you help in writing this. So there's a lot of things sort of missing from that. And this mostly exists because it was needed to build CPython. And not a lot of work is going into sort of expanding this or adding anything to this. Nothing has really been added to this. Most of the focus is on the pure Python packages part of setuptools. So everybody has to sort of reinvent the wheel. Ignore the pun. In fact, NumPy, for example, had over 13,000 lines of code dedicated to just patching up and working with distutils. And so this becomes even harder if you're a package trying to extend this and add some of that functionality yourself. This is a complex system because setuptools is built on top of distutils. It's hard to debug this and figure out where things break. It's very fragile because it doesn't really have a public API. Sort of separation between private API. But there were some, and there still are some scikit-build the classic version was built as sort of a hack on top of setuptools, and there's some others too, some that are actually quite nice, like setuptools Rest. We've shipped one in PyBind 11 for quite a while. So, but this is all changed in 2017 when PEP 5.17 came out, and this came up with a simple standardized API for builders. It supported installing build requirements, so now you could say, hey, I want setuptools, or you could say I want something that's not setuptools. And even the build backend can say, hey, I need these dependencies. And it can dynamically decide to do that. And the backend is responsible for everything. I'll show you the hooks in just a second. The backend really does everything. It is responsible for producing the output files. And editable installs were added to this later. So this is the collection of hooks. It's not very many. There's only 2 required ones: build sdist, build wheel, and they do what you think they do. You say, please build an sdist, please build a wheel, and the backend does it. So the backend can take over all of this. In fact, it doesn't even need to be written in Python. It just has to have a Python API here to call. So it also gives the ability to dynamically request dependencies. You can say, hey, what do you need to build an sdist? And it can tell you. There is a mechanism now for editable installs. There's also a mechanism to just ask for the metadata without building a wheel, that one's been a bit tricky to support sometimes. So this is sort of what I would consider the new era of Python packaging, where we now have builders that will use this interface and build sdists and wheels. So 2017 was sort of the first one with Flit. It was originally Flit. Anything with the star there got renamed later, but that's the current. I've used the modern names. So Flit came along in 2017. Poetry came along in 2018. PDM PEP 5.17 came along in 2020. And Hatchling came along in 2022. And setuptools moved over to using this mechanism, or supporting this mechanism in 2022 as well. But binary ones were a bit slower, and adoption's been a little slower because there's a lot more to building a binary. There actually was one originally, this Inscons. I want to give a shout out to that, even though it's not really very actively developed anymore. But it was sort of the first one in this space. Maturin came along, and then meson-python, scikit-build-core was ones that I've been a bit more involved in. Were just about 2 years old or so. And they were just beginning to appear last time I spoke at a PyCon. So meson-python was a project that started because of SciPy and NumPy. And they saw Python 3.12 coming. They panicked because because of their 14,000 lines of code that was wrapping distutils, that didn't actually work with the distutils that comes as a third-party library. It only worked with the one that was built into Python. And so they were somewhat panicking here. And they said, well, this is a perfect time to just update, go to something new, and get rid of this. So SciPy and NumPy spurred the development of meson-python, which uses the Meson build system and wraps that in Python. And NumPy was able to take their 13,000 lines of code down to 2,000, not counting the fact that they vendored Meson and forked it in, and that's 100,000 lines, but we won't talk about that. So the Meson build system just needs 3 files. It does also require they have Git set up. Meson will complain. You have to, I think there's some extra configuration you can do to avoid Git, but it'll expect it by default. We're just going to write a little PyBind 11 file. That's going to be in our example CPP. And then in order to configure this from Python, we just need a pyproject.toml file that looks like this. You just say that you need meson-python and PyBind 11. Your backend is meson-py. And you don't need there's no other required configuration there. And then you write a Meson file, meson.build. It looks like this, where you set up your project. You tell it to find Python. You get the PyBind 11 dependency, which is now, they built in support for PyBind 11. This is why that is now quite simple. And you make your extension module. Okay, so it looks something like that. Then you just run, you can do pipx, run build, installer UV if you want to use that, and it'll build. So there are several features that PyBind 11 gives you. You can actually skip the that name table. I showed you a name table here. Oops, I didn't realize I did. That project name and version, you can actually skip that part for very, very simple projects. There are some options that you can specify in PyProject Atomo and config settings. It has really good editable install support. It will only add Ninja if that's missing. That's something that I helped add that was very important to make this work well. And free-threaded Python support was added relatively recently. Now, the one that I know that I'm the most involved with is the one in scikit-build. I'm part of scikit-build. Scikit-build is actually a family of tools. I list some of the ones there, including if you do pip install Ninja or pip install CMake, you're actually getting that from us. And it also had this scikit-build tool, and I put in a proposal and got funded for 3 years to work on rewriting this for the modern systems, and that's scikit-build-core, which is not yet the core of scikit-build classic, but eventually that'll also be replaced. So with scikit-build-core, again, we have our little file. It's still there. We just use scikit-build-core now inside of our build system, and now we write a CMake file, because this is an adapter for CMake. We have the project and minimum version. In PyBind 11, for historical reasons, you have to ask for the new Python support, and then you add a module and install it. Okay. And this also supports like free-threaded Python, and PyBind 11 doesn't, but the build system does. And it supports editable installs based on the initial implementation in meson-python, and a variety of other things. So again, it automatically includes CMake only if it's not on your system. So you can build on a system that doesn't have a binary for CMake, like FreeBSD, for example. You can just install CMake, and then the system will still work. And we have great support for a variety of different things there. Looking at a little peek into the internals, because this is one of the things I really like inside the internals. This is the way that the configuration is actually set up. We have over 40 configuration options, and it's really just this nice declarative data class structure where we have each of the different settings, and it's here. And then all of this then can be fed in to generate a JSON schema, which we publish to the schema store. This generates the README you see, and Cog produces this section in the README from this. We support reading anything in from PyProject Atomo or through config settings, which is the -c flag in pip or build, and environment variables, all from this one definition, which is fun. So these are some of the examples of the options here. One really interesting one is this minimum version, where if you set your minimum version, we will actually make sure that none of the defaults and things change, and that will continue to work. So if we do change a default, that minimum version protects you just the way that it does in CMake. CMake has the same idea. And there's a variety of other things that you can do here. You can set your CMake defines in this table here at the bottom. There's a variety of different things you can do. One thing that we support that has been, I think, a really nice addition to scikit-build. Somebody initially contributed this. And this is the idea of these dynamic metadata plugins. So for example, if you want to use regular expression to pull in the version from some file in your code and then use that, you could do that this way. And then I'm actually working on trying to standardize this so that other build backends can use it. So if you're interested, go to scikit-build/dynamic metadata, and there's some API design ideas there that we're discussing. So feel free to join in if you have opinions. And we can also generate this. So for example, this generates a file only into the wheel. It does not show up anywhere else. But you can actually target the CMake build directory, just the wheel, the install directory, or the source directory, the way that it's often done today. This is a really nice feature. In scikit-build-core, we also have this overrides mechanism. It was based on CI-build-wheel's override mechanism, which in turn was based on MyPy's overrides mechanism. That one I didn't write, but I wrote the other two. The way that this works is it matches top to bottom. Each of these this double square brackets is an array in Toml. And it matches down. And so if the platform system is Mac OS, if it's Darwin, then it will apply the different CMake version. So you can do a lot of configuration here using this. There's a bunch of different options for things you can check. You can even base this on environment variables, which you see at the bottom. It does support the inherit, which was also added to CI build wheel, so you can tell it to inherit from a previous one instead of overriding it. You can also just set it to true, and that will do like truthy, falsy matching for like environment variables. Scikit-build-core is the recommended way to build with nanobind. So this is actually an example pulled from the nanobind example, if you look at the official nanobind example. And what it's doing is actually it does something kind of interesting. And this is actually pretty much the entire thing, minus a couple comments. It's setting this wheel.pypi to 3.12, CP3.12. That means it will use the stable ABI of Python if you build for 3.12. So therefore, that wheel will work on 3.13 as long as you don't turn on free-threaded mode when you compile Python. And before that, it'll just build regular wheels, because 3.12 is the first version that nanobind supports the stable ABI for. So that's a really nice feature there. That's handled inside the CMake nanobind helpers as well, and that'll build wheels for all the different platforms. There's some projects using scikit-build-core. Rapids AI is using scikit-build-core. They actually added a file generator to generate this across all their different projects. I have a couple examples. So PyZMQ is using it, and that's the example of their configuration. And then we also use this for CMake. This is a particularly fun one because we are CMake. So for example, we have to make sure we disable the CMake version check because we are CMake, so we can't ask for CMake, because that would be asking for the package that we're building. So this is now the pip install CMake package you get is built with scikit-build-core. We also have support for plugins. This was meant to be a tool that could be used to write plugins. So this is the hatchling plugin. Currently it's built in. If you do use it, we recommend limiting it to just scikit-build-core 0.9 because we're going to pull it out into its own separate plugin. But this allowed us to more quickly iterate between the plugin and then the API the plugin is using. And you can build a project in hatchling just as if it was a pure Python project, but also add a CMake-based extension to it. And it currently requires the experimental true flag, which is basically just saying that, yes, I understand, I need to limit scikit-build-core that way. Okay. As part of the scikit-build project, I've been playing around with statistics. You notice I quoted a few. If you want, they're actually at that first link there. You can look at the source to produce these. So this is a look. One of the things I do regularly is I download every pyproject.toml off of PyPI. And then I can look at all sorts of different stats. There's tons of really interesting stats when you have the entire collection of every pyproject.toml that's on PyPI. For example, I can tell you exactly how many scikit-build-core projects there are, meson-python projects, or maturin, because I just check for those strings. And then I can combine that with the top PyPI packages, and there's the list of packages using them. And maturin has been around a bit longer and has a bigger list. But total downloads is dominated by the scientific Python ecosystem, which is like the top 6 things there. But I know some more coming. But that's an interesting thing you can get from this. Another thing you can do is you can say, well, what are the most popular tool sections? I use this to help Schema Store in deciding what schemas they need to work on and getting into Schema Store. And I think I've put in about half of them as well. You can look and see how people are making typos in their pyproject.toml. They're at the 1% to 2% level. There's a ton of typos in pyproject.toml. Nothing happens if you accidentally stick something that's not allowed, but anything that's grayed out there is not allowed. In fact, I've used this for a variety of different packages. Like I gave the black authors were interested in this, and I helped them evaluate the impact of a bug by basically looking at the contents of the line length section. And I can also see how many people have made typos on line length and aren't actually setting a line length when they think they are. I can look at scikit-build-core, of course. So this is an example of what people are setting for their minimum version. I can look at what people are setting, how they're using the PyPI field. I can look at what fields they're using and how many, and I can even ask questions like which packages are actually doing this. Okay, and then moving on from scikit-build-core, the maturin is a tool for Rust, or maturin, I don't know exactly how to pronounce it. And Same sort of thing here. Of course, we have Rust now with the excellent Pyo3 library. And then we again have our PyProject.toml, which looks pretty similar, except we're using maturin now. And then you have a cargo.toml, because this is using Cargo's package manager. And this is sort of an example setup for the thing that you see there. And you can either build this the regular way, or maturin can actually build this directly. And that's because maturin is written in Rust. And if you're building packages, you don't always even need to touch Python at all to build a Python package, because it can build the SDist and wheels for you. So it can build it without Python. And if you're targeting the limited API, it doesn't need Python at all. And Rust has a fantastic build. The configuration build of Rust is fantastic. In fact, if I were to list of reasons why I would use Rust, I would say this is probably the list that I would make. Rust in Cargo is just so fantastic. It's great for cross-compiling. The tooling around this is all really, really good. This single binary approach works really well making wheels, and yeah, there's some memory safety stuff or whatever there, but that's secondary. This is so good. And this includes maturin action. So you can use CI-build-wheel. We just added an example for CI-build-wheel and maturin, but you can also use maturin action. And you are going to, that's specifically for maturin, and that's specifically for GitHub Actions, but it can do some very nice things like cross-compile, which saves you a ton of time. It actually builds. So on the top here, you see it's building all the Rust dependencies, and then it's only rebuilding the Python parts for each Python version you're targeting. So the stable ABI, and then PyPI 3.7, 3.8, it's going through each of those. Very, very nice, something you can't really do. There's actually one platform that you can't get with CI-build-wheel that you can, just because Rust doesn't provide 32-bit musil wheels, or 32-bit musil binaries for Cargo. I just want to finish up with a couple of mentions for related things that I think are really useful to have. The Scientific Python Development Guide is a fantastic resource for all sorts of projects. It's not scientific specific, but it includes scikit-build-core, meson-python, and maturin tabs that you can switch through, along with a lot of other things. It also comes with, it's integrated with a cookie cutter, which supports 11 different backends, including the ones I've talked about. You can use cookie cutter or copier. It's not a package I know that does both. And it's in sync, and everything is tested by Knox. And it also comes with a WebAssembly repo review tool, which allows you to then check your repository and see how closely you're following. And all of these are cross-linked. You can just click on the link, and it jumps you straight to the developer guide. And that works in the terminal, too, by the way, the linking, which is a fun feature a fun feature. Okay. So overall, I think a lot of things have changed over the past 2 years. These backends are just really, really fantastic, and they're now available for making binary projects. You don't have to be an expert in this to write a little bit of C or Rust or C++ code now to accelerate a small piece, and you don't have to worry about if users can get that or not. And we've got these sorts of resources, and you can ship these really well. Just want to say thanks to all the people that made this possible. I'm a member of these teams, but there's a lot of other people on the teams, scikit-build team, the meson-python team, and the CI-build-wheel team, specifically for all the work that they've done in making these sorts of things possible. And I'm not on the maturin team, but definitely thanks to those for making a really, really fantastic tool. Okay. All right. And with that, do I have any questions? I think I was told I had 30 minutes, so. I think there is a mic there if somebody has questions that you can go to.
So usually I build wheels and I also build conda packages. How does it integrate with building conda packages?
So for the conda package, so the conda package would sort of you would need some mechanism to build that. Conda forge would be the standard way to build that. That sort of replaces, or you could put that in the same place that CI build wheel was in. All of these tools do integrate well with that. We've had to do some work. It was actually easier for meson-python because they didn't have a lot of existing meson support in Conda Forge, but unfortunately, a lot of weird CMake variables are set in Conda Forge, some of them incorrectly. So we had to do some work to make sure that scikit-build-core would smoothly build Conda packages, but it does.
Hey, so are we done? Sorry, I'm here. So the question is, what's any more feature gap that you think exists, or are we done? Is the problem solved?
What do I think would be coming?
Yeah, next up, or what do you
What's
think
next?
is still next?
I have a long list of things that I still would like to work on for scikit-build-core. One of the main ones for me is that I would like to have it replace the build backend for scikit-build so that I don't have to maintain two of them. So that's something I'll be working on. So that means the setuptools plugin, that does also have a setuptools plugin, will be finalized, probably moved to its own repository. And that's probably the point that I would actually call it 1.0. But there still are other things. Most at this point, though, I'm basing the development a lot more on packages as they adopt scikit-build-core to see what they need. So one thing I do not support is sort of just free dynamic Python at this point. I would much rather see if there's a static way to solve your problem versus just giving you a hook that you can use to do whatever you want. You can always write a plugin, but so far, even for fairly large projects, I haven't seen a need to go beyond the 40 options or so that we have. Yes?
Great. Thank you for a great presentation. My question is kind of twofold. So you mentioned the dynamic metadata, and as I'm aware, there's also a dynamic keyword under the project section in PyProject TOML. I was wondering if you could describe what the differences are there, and if there's
Yeah, there's several things. So when I was speaking about dynamic metadata here, that was really referring to that dynamic keyword. So in scikit-build-core, you can specify, you would specify dynamic equals something. So let's say you wanted to do version. What was my example I have here? Probably version? Yeah, version. So here you would say dynamic equals bracket, quote, version, quote. And then there are several built-in plugins, and people can write plugins that allow you to run pretty much anything you want to produce that metadata. You can actually write your own. There's a way to make this a local path, and you can literally write whatever code you want. I'm hoping that this will become standardized, and there will be a tool.dynamic metadata section for this, and multiple backends will be able to use the same plugins. But that's referring to this. You would have to list version in the dynamic list. There's also metadata itself can be dynamic, which means it can change from the estis to the wheel. And the dynamic metadata plugins have support for that. But there's still some rough edges to work out there. It is built into the API here, but there are some tricks with that. But yeah, that is what this means. It's a way for you to write your own metadata producers. So there's built-in ones for setuptools SCM and for fancy PyPI README. Those two are built in. And I would like to have those packages actually support this. I'd like to make this a standard, have those packages support it, and then add support to meson-python, to hatchling, to all these other packages.
That answers my second question. Thank you.
It's incredibly handy, by the way, to be able to produce this if you need to. And
Hi, can you use any of this to make an executable?
Sure. Okay. Yes. So you can. You definitely can. In fact, several of these things were executables. If I had the list, I was later. Sorry. So in this list, a lot of these things were executables. CMake, of course, is an executable. And so you basically just tell it to write to the Cling format may not be quite high enough to be on that list, but Cling format. Oh no, Cling format's right there. That's an executable. That's Cling format. So you trigger the CMake based build system. You don't have to rewrite the build system. You just trigger the CMake based build system, and then you can target where to put it, or you can move it to the bin folder if you want, or you can write some sort of wrapper or entry point if you'd rather. It's usually you can just write it to bin if it's a binary, and then you can ship that fairly easily. So if you have an existing tool that already uses CMake, it's really trivial. It's under a page to set this up to now ship that on PyPI. And Clang format would be probably the one I would go as an example. You can look at CMake, but again, that's a tiny bit more complicated just because CMake is CMake. So you've got kind of weird circular things going on there. A lot of the ones in Maturin are also done that way. It has very trivial support for saying, here's a Rust binary, ship it.
Got it. Thank you.
Great talk, thanks. So my question is, we're talking about binary builds, and Python's a big C project. Could we hypothetically use something like this to build Python itself? Maybe even like a statically linked version of it?
Try, I think it's pip install Python -distribution. I don't remember. Last PyPI 2 years ago, when I was showing this in at PyCon, someone like the next day produced exactly that. So you could, and that sort of, I think that sort of went into the PyBI type projects and stuff that people have been working on. But you can actually ship Python this way.
Cool, thanks.
Yeah, it's Python something, but it's on PyPI.
Hi. I'm afraid my question might be explicitly beyond the scope of your talk if you wanted to avoid like packaging systems or metadata and naming schemes, but one of the coolest things about scikit-build-core right away was with the CMake support, you could easily have a lot of flexibility for the environment in which you're building and do a lot of variations on your build that aren't representable in the or to the Python package installers. Mm-hmm. Can you comment at all about anything that's happened in the last year or two, or anything that you see on the horizon that's going to make it easier to distinguish unconventional binary differences, maybe differences in dependencies or system libraries, things that tend to be more important in scientific computing packages that are based on compiled libraries and things like that?
Yes, so I think one recommendation would be to go to the packaging summit tomorrow afternoon. There are some various proposals talking about ways to do this. I know that there's a lot of interest, say, for supporting CUDA, better support for CUDA on PyPI, things like that. It certainly does give you a lot of freedom to make your own custom builds. In fact, it's not hard to set up your build so that you can build it directly or with scikit-build-core, which then means you can do whatever you can do with a normal CMake build. Maybe that would integrate better with your with how you build in your package manager, for example. Very similar to the way that you also see this with, say, Rust packages, where you can build with cargo. A lot of tools also support building with cargo, or maybe shipping with cargo, and support making something with Maturin. So I'd say most of that is probably most things that will be discussed probably in the packaging summit. So there are proposals. I've seen a couple of proposals on ways that to sort of improve that. But I don't know if I have much specific I can say about it, though. Yeah.
Well, thanks for your great work anyway.
Thanks.
For the, when you're shipping executables like Ninja or something, does it work best with things that build themselves with CMake, or can you use it to build like an AutoTools project or something? Like, how does that work if you want to build an executable that isn't built with CMake?
If you're building something that's not built with CMake, I would generally, usually the way you'd probably want to do that would be, if it's built with auto tools, your best sort of cross-compatible way to do this would be to go ahead and write a CMake file. You can do that inside of your wrapper. It's, of course, easier and nicer if the upstream just supports it. The problem with triggering and calling a wrapper is that you have to make sure that it's available and things like that. Now, what I would do if I was going to ship, say, an AutoTools wrapper, I think the way I would probably try to do that is to write a hatchling plugin. Because hatchling, I'm currently working on improving the support for hatchling and targeting different systems and stuff. So hopefully it's sort of auto tag generation stuff will get a little bit better in the next month or so. And that has very simple support for calling something and then running. So I've helped convert somebody, Charlie Marsh, I think, actually, had a package that was distributing something, and it was written as a hatchling plugin that was just trying to manually call a make file. And I was like, well, the thing you're wrapping has a CMake list. Why not just use that? I converted it over to scikit-build-core, and it was much simpler. It automatically supported Windows for free. It was way better. But that's sort of the approach I think I would take. Though I do think hatchling sort of support for binary tags and stuff should improve, which I think it will soon.
Okay, thank you.
We have a couple minutes left if anybody has a question. Otherwise,
I think I thought was under the impression that it was 30 minutes instead of, I guess maybe it was 45 minutes. But I was told it was 30 minutes before it started.
yeah.
But that's good. We've had lots of questions.
All right, let's give Henry a hand.